How long do you really think it takes to get to another planet? Not in theory, but in actual days and years of your life. You probably started this video expecting one clean answer, like Mars takes this long, Jupiter takes that long, Neptune takes that long, as if there is one correct number for each world. But the first thing you have to face is simple and uncomfortable. There is no single number. NASA saying Mars is about 7 to 10 months, or Jupiter is about 5 to 6 years, is not a law of nature. It is a summary of what we can do with the rockets and the money we have right now. Any of those and the time changes too. When a space agency publishes a travel time, it is quietly assuming a lot of things. It assumes chemical rockets, not nuclear ones. It assumes a certain type of trajectory, usually one that saves fuel, not one that saves time. It assumes a certain launch window, when the planets are in a useful alignment. It also assumes a certain risk level, how hot you are willing to run the engines, how much stress you accept on the spacecraft, and how much margin you want for backup systems. So when you hear 7 months to Mars, what you're actually hearing is, with this engine, on this trajectory, at this cost with this level of risk, it takes about 7 months. So if the time is not fixed, what is messing with it? First, the distance itself refuses to stay constant. Earth orbits the Sun at about 93 million miles out. Mars is farther out, but the distance between Earth and Mars is not one number, it is a range. On average, we say Earth and Mars are about 140 million miles apart, but sometimes they are much closer, around 34 million miles, and sometimes much farther, more than 200 million miles. That gap is always changing because both planets are moving around the Sun at different speeds. The same thing is true for every planet. Venus swings closer and farther. Jupiter does the same. Saturn, Uranus, Neptune, all of them are moving targets. That means you cannot just say Mars is this many miles away, the rocket goes this fast, so the time is distance divided by speed. The path is not straight, the target is not still, and you are not free to launch on any random day. What really sets the clock is orbital geometry, the exact shape and tilt of the orbits, and the timing of your launch window. You wait for a time when leaving Earth on a certain curve around the Sun will let you cross the orbit of another planet at the same moment that planet is there. If you launch too early or too late, you miss that intersection, and you either burn more fuel to correct, or you accept a much longer trip. Even if you pick the perfect day, you're not free to just keep pushing faster and faster. A spaceship is not powered the way a jet is, where you can just keep burning fuel all the way. To leave Earth at all, you need to reach something close to 25,000 miles per hour. That is the rough speed you need to escape Earth's gravity. To get that, you rely on chemical rockets, which throw exhaust out the back at a few miles per second. That exhaust speed gives you a limit. It tells you how much you can change your velocity before your fuel tanks run dry. The more you try to speed up and slow down, the more propellant mass you must carry, and that mass itself needs more fuel to push, so the problem grows fast. This is why, even though the raw distance to a planet like Saturn is only around 1 billion miles at certain alignments, we still talk about travel times of 6 or 7 years. You get a few strong burns, usually near Earth, maybe near other planets for course changes, then you coast for a very long time at tens of thousands of miles per hour. You spend almost the entire mission on what is basically a controlled fall around the Sun, following a curve set by your last big burn. You do not have the fuel to constantly accelerate and decelerate the way science fiction often shows. With chemical rockets, continuous thrust is simply not an option for long periods. So let's strip away the theory and look at what has actually happened. Mariner 10, which flew by Mercury in the 1970s, needed around 5 months from launch to its first Mercury encounter. That sounds reasonable, fast even, but it was a flyby, not an orbital insertion. It raced past the planet and kept going. Messenger, which was designed to actually orbit Mercury, launched in 2004 and did not enter Mercury orbit until 2011, about 7 years later. It used multiple flybys of Earth, Venus and Mercury to slowly shift and reduce its speed enough to be captured by Mercury's small gravity field, because doing all of that braking with fuel alone would have been too expensive in mass and money. Move outward. Cassini, the famous Saturn mission, launched in 1997 and arrived at Saturn in mid-2004, about 6.7 years in transit. Again, not a straight shot. It used a sequence of gravity assists, including Venus and Jupiter, to build up the right speed and direction, go even farther. Voyager 2, launched in 1977, reached Uranus in early 1986. About 8.5 years later, then Neptune in 1989, around 12 years after launch. Those are not estimates or marketing numbers, those are stamped into the actual telemetry, real clocks that ticked, while a real spacecraft moved through space. Every one of those timelines, 5 months, 7 years, 6.7 years, 8.5, 12, came from trade-offs. Mission planners balanced fuel mass, launch vehicle power, gravity assists, planned science at each stop, and acceptable risk. Want to cut a year off the transit? Maybe you need a bigger rocket, or you lose a gravity assist, or you arrive going too fast to easily break into orbit. Want to save money on the launch vehicle? Maybe you add an extra gravity assist, which adds 2 more years of travel time. Time, fuel, and risk are locked together. When you pull one, the others move. So what are you really asking when you say, how long does it take to reach a planet? You're not just asking for a number of days, you're asking, with what engine, on what path, with what budget, and with what level of fear? If you stick with today's technology, chemical rockets plus some small electric thrusters, and today's budgets, you get Mars in about 7 to 10 months, Jupiter in around 5 to 6 years, Saturn in almost 7, Uranus and Neptune in around a decade. If you imagine stronger propulsion, like nuclear thermal rockets, or advanced ion drives with much more power, you can cut those times sharply in principle. Mars drops from months to maybe a few weeks, Jupiter from years to maybe around 1 year, Neptune from 12 years to 1 or 2 years, if you are willing to accelerate and decelerate for long stretches. That is the uncomfortable truth behind the simple question. The solar system feels huge right now because of the engines we choose to use, the money we decide to spend, and the risks we accept. Change those and the same distances suddenly fit inside one human career, or even inside one long mission. So when someone says, it takes this long to get to Mars, you should always ask back, with what technology, and how hard are you pushing it? And if time and space is really controlled by how fast you can change your speed, and how much speed you can afford to buy, then the next thing you need to understand is very direct. With the rockets and propulsion systems we have today, what is your real speed limit, and how much solar system can you actually reach before the clock beats you? What does fast actually mean for you once you've already left the launch pad? Once you're really in space? You might think once the rocket is done and the engine's cut off, the hard part is over. But in orbital mechanics, that moment is basically just the starting line. Your first real milestone is low Earth orbit, moving at roughly 17,500 miles per hour, circling the planet every 90 minutes or so. At that speed, you're not going anywhere else yet, you're just falling around Earth forever. Not falling down, not escaping, just stuck on a loop. From that parking orbit, every serious trip to another planet starts with one more big decision and one more big burn. You fire your engines again, not for as long as the launch, but at a very precise point, in a very precise direction. That burn adds a few thousand miles per hour to your speed, changes the shape of your path and stretches your orbit from a circle around Earth into an ellipse that reaches out toward the rest of the solar system. That is the moment when I'm orbiting Earth turns into I'm on a transfer trajectory to Mars or Venus or Jupiter. Without that extra push, you never leave the neighborhood. So how fast are we really talking when we say deep space? If you look at shuttle class speeds, around 28,000 miles per hour relative to Earth, and you do a simple rough calculation, you get some surprisingly short times. The speeds in that range, a simple straight line estimate gives you something like 210 days to reach Mars, on the order of 1.9 years to reach Jupiter, and around 3.6 years to reach Saturn. These are not exact mission designs, they ignore orbital geometry and braking, but they give you a feel for the scale. At that kind of speed, the inner planets are months away. The gas giants are measured in a few years, not multiple decades. Now push harder. Some interplanetary missions have left Earth moving at effective speeds of around 54,000 miles per hour or more. Galileo to Jupiter is a good example. If you imagine keeping that kind of speed across the whole route, those travel times drop sharply. Jupiter shrinks from almost 2 years to somewhere near 1 year. Saturn falls from more than 3.5 years down toward around 1.8 years. Again, these are rough back-of-the-envelope numbers, but they are enough to expose the main point. Doubling your speed does not make the solar system small, but it absolutely pulls it into a range that fits inside a human timeline. So why don't we always aim for the higher numbers? Why not just push every mission to the edge? This is where you run into the thing that really controls your schedule, your delta V. Delta V is just a shorthand for change in velocity. It is the total amount of speed change your rocket can give you. When you add up every burn, every course correction, every braking maneuver, you can think of it as your propulsion budget. More delta V means you can launch faster, bend your trajectory more aggressively, brake harder at the target, or carry more margin for emergencies. Less delta V means you have to be careful. You follow the cheapest, slowest trajectories, you lean on gravity assists, and you accept very long coasting phases where you do not touch the engine at all. Here is the key. The time to a planet is basically a function of 3 things: the orbital geometry, the trajectory you choose, and the delta V you are willing to spend. A minimum energy path, the classic textbook Hohmann transfer, uses as little delta as possible to move from one circular orbit to another. It is efficient, but it is slow. A high-energy path spends extra delta V to leave faster, reach the other orbit quicker, and sometimes arrive going faster too, which then forces you to spend even more delta V to slow down. In almost every real mission design, someone sits down and says, here is the distance, here is the delta V this rocket can realistically provide, so here is the travel time you are stuck with. If it is so simple, why not design a ship that just keeps accelerating? After all, if you could keep pushing at even a tiny fraction of Earth gravity, just a few % of a G, you could, in principle, reach Mars in weeks, not months. The physics for that is not exotic. Constant acceleration for half the trip, then constant braking for the second half gets you there very fast. The problem is not the math, the problem is the fuel. Chemical rockets throw mass out the back at a few miles per second. If you try to run them for long periods, your propellant tanks explode in size. The more fuel you add, the heavier the ship becomes, and the more fuel you need just to move the fuel, and it spirals out of control. That is why real missions accept slow, patient, low-thrust profiles. They use a handful of strong burns, then coast for months or years, then burn again to brake into orbit or to adjust the path. A Mars mission with today's chemical propulsion accepts a 7 to 10 month transit, not because we love waiting, but because trying to cut it to 3 weeks with current engines would require a completely unrealistic amount of propellant. A Jupiter mission takes 5 to 6 years, not because Jupiter is far in some emotional sense, but because shaving that down to 1 year with chemical rockets would demand a rocket stack and a budget that nobody is ready to approve. So now you can see the pattern forming. Your starting point is low Earth orbit at about 17,500 miles per hour. Your realistic deep space cruise speeds live somewhere in the tens of thousands of miles per hour range, and your true limit is your delta V budget, not the raw speed number on a chart. With modest delta V, you're stuck with gentle, curved minimum energy transfers and long travel times. With larger delta V, you unlock steeper, faster paths, you can ignore the slow highway and cut diagonally across the solar system. And this is where the tension really starts to climb, because once you understand what your engine can actually do, every planet becomes a challenge. Same physics, different target, different trade-offs. How fast can you realistically reach Mercury if you must also slow down enough to orbit it? How short can you make a Mars trip before radiation and fuel become serious threats? How much time are you willing to spend coasting in deep space to reach Jupiter, Saturn, Uranus, Neptune, without pushing beyond today's propulsion? You're about to play mission planner for the whole solar system, and now you know the rules, your speed is limited, your fuel is limited, and your clock is always running. The only question is, when the launch window opens for each world, how much of your life are you willing to trade to get there? What if the real deadline for your trip to Mars isn't the launch countdown on the rocket, but the position of the planets months earlier? You probably imagine that once you build the ship and roll it out, you can just pick a date and go. In reality, you don't leave when you feel like it. You leave when the geometry of the solar system allows it. For Mars, the best launch windows open roughly every 26 months. That's a little over 2 years. If you launch inside that window, you're about 7 months to Mars number holds up. Miss it, and that same trip starts stretching toward a year or more, or it becomes so expensive in fuel that it stops making sense. Here is why that happens. Earth and Mars are both moving around the Sun on elliptical orbits, at different speeds, at different distances. To move from Earth's orbit to Mars's orbit in a fuel-efficient way, you don't fly straight at Mars. You leave Earth on a curved path around the Sun that will intersect Mars's orbit at a very specific point. Mars has to be at that point at the same time you arrive. If you leave too early or too late, your path and Mars's position don't line up. Now you have a choice. Either you burn a lot more fuel to change your path in flight, or you sit on a slower, less efficient trajectory and accept extra months in space. This timing rule doesn't just apply to Mars. Every planet has its own rhythm of launch opportunities. Venus has its own pattern, Jupiter has another. The outer planets each have long spaced out windows where a transfer orbit makes sense. The orbits set the schedule. You either respect it or you pay in money, mass and time. So what's the cheap way to go? The method that shows up in every orbital mechanics textbook. That is the Hohmann transfer. It is the minimum energy path between two circular orbits in the same plane. In plain language, you start in one orbit. Do one burn to jump onto an elliptical orbit that just touches the orbit of the target world. Then you do a second burn at the far end to match that new orbit. If you are going from Earth to Mars, that ellipse stretches outward to Mars's orbital distance. If you are going from Earth to Venus, it stretches inward instead. The important point is, this path uses as little delta V as possible, which means less fuel, smaller rockets, and lower cost. The classic months to Mars, years to Jupiter numbers mostly come from these Hohmann-style transfers. For each planet, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, you can write down a Hohmann transfer time, how long it takes to ride that minimum energy ellipse from Earth's orbit to the target orbit. When you compare those ideal numbers to actual low-cost missions, they line up fairly well. Real missions have complications like orbital inclinations and small course corrections, but the general scale matches. That is why those textbook times are still useful. They tell you the basic, slow, cheap highway through the solar system. But what if your rocket doesn't have the delta V to brake efficiently when it reaches the target? Or what if slowing down purely with fuel would demand a ridiculous amount of propellant? This is where gravity assists come in, and where you start trading fuel for calendar years. A gravity assist is simple in concept. You swing past a planet and its gravity tugs on you. Relative to the Sun, you can steal or shed some orbital energy. Your speed and direction change, and you didn't have to burn fuel to do it. Look at missions to Mercury. Messenger and Bepi Colombo both use long chains of gravity assists. They fly past Earth, then Venus, then Mercury itself multiple times. Each flyby slightly reshapes the orbit, shaving off speed as they fall deeper into the Sun's gravity well. The goal is to arrive at Mercury slow enough to be captured into orbit without a gigantic braking burn that would require a huge fuel load. The penalty is time. Instead of a simple fast flyby in a few months, you get roughly 7-year travel times to a planet that, at its closest, is only tens of millions of miles away. The same trick works in the opposite direction, for missions heading outward. Venus flybys, Earth flybys, and Jupiter flybys can all be used to boost a spacecraft's speed and bend its path farther out. Voyager, Galileo, Cassini, Juno, New Horizons, they all used gravity assists to get more free speed than their launch vehicles alone could provide. Again, the cost is time. You spend extra years setting up those flybys, but but you save enormous amounts of fuel. So what happens if you mess up the timing, or you choose not to wait for the perfect alignment? If you launch late for Mars, even by a few months, your carefully planned transfer arc no longer hits Mars cleanly. Now you either pay with extra delta V mid-flight, burning more fuel to change your path, or you accept an arrival that is slower and harder to break into orbit. In practical terms, your 7-month cruise can turn into a 10, 11 or 12-month cruise. That is why when people quote how long to Mars, they give a range, roughly 128 to 360 days, depending on the year of launch and the exact trajectory. This is the quiet pressure behind every interplanetary mission, the clock you can't argue with. The planets move, the launch windows open and close. If your rocket, your spacecraft, or your funding is not ready on time, you do not just slip the schedule by a week, you can slip by months or even by more than a year, waiting for the geometry to line back up. The solar system does not care about your project timeline. Now put all of this together with what you already know. Your speed is limited by your propulsion. Your total velocity change is limited by your delta V budget. Your launch date is limited by the positions of the planets. That means every how long does it take to get there question is really, with this engine, at this launch window, on this trajectory, how many months or years are you stuck in deep space? With that in mind, it is time to stop talking in generalities and start pushing numbers onto specific worlds. You know the rules, you know why the windows matter, why the orbits matter, and why the engine matters. So here is the next uncomfortable question. If Mercury is the closest planet to the Sun, and sometimes not even that far from us, why do missions that actually want to orbit it take almost as long as missions to Saturn? How can the closest planet end up taking almost as long as a trip to Jupiter? On paper, Mercury looks simple. It never gets more than about 133 million miles from Earth. It's the inner neighbour. It feels like an easy first stop. When you look at the missions that actually tried to orbit it, you hit a wall. Messenger took about 7 years to get into Mercury orbit. Bepi-Colombo is also on roughly a 7-year path. Those are Saturn-style travel times to a planet that is, in raw miles, much closer. That is your first big reality check. Distance by itself does not tell you how long the trip takes. The core problem is not getting to Mercury, it is slowing down enough to stay there. When you drop inward toward the Sun, gravity pulls on you more strongly. Your spacecraft speeds up as it falls deeper into the Sun's gravity well. That extra speed is great if you only care about getting there quickly, but it is terrible if you actually want to be captured into orbit. To get into orbit around Mercury, you have to cancel a huge amount of orbital energy. In plain terms, you have to slow down a lot relative to Mercury and the Sun. If you tried to do all of that braking with chemical rockets alone, you would need a ridiculous amount of propellant. Every extra pound of fuel makes your spacecraft heavier, which means you need more fuel to push it, which adds more mass, and the spiral keeps growing. At some point, the rocket you would need becomes too large, too expensive, or simply not possible with current launch systems. So instead of paying with more fuel, Mercury missions pay with more time. This is where gravity assists and long looping trajectories come in. Mariner 10 back in the 1970s is a good baseline. It took about 147 days to reach its first Venus flyby. After that, it went on to make flybys of Mercury. The total time to that first Mercury encounter was on the order of a few months, which sounds fast. But Mariner 10 never tried to slow down enough to orbit. It used Mercury as a flyby target, not a final parking place. It flew past, took data, and moved on. Compare that to Messenger. It launched in 2004 and only slipped into Mercury orbit in 2011, so roughly 7 years from launch to orbit. In that time, it performed one Earth flyby, 2 Venus flybys, and multiple Mercury flybys. Each pass was used to adjust its path and shave off speed relative to Mercury. Bepi-Colombo, launched in 2018, follows a similar pattern. Its plan to arrive and enter orbit around Mercury in 2025 also works out to about 7 years. Same target planet, same basic distance, totally different timelines, depending on whether you just zip past once or whether you slow down enough to stay. If you were riding along on one of these missions, your trip to Mercury would not feel like a direct fall toward the Sun. You would see a series of long, stretched out orbits, first around the Sun near Earth, then past Venus, then dipping in closer each time. You would cross the orbit of Mercury over and over again, each flyby changing your speed and direction a little bit. The path would look like a twisted spiral inward, a helix of orbits slowly tightening around the Sun until you finally arrive slow enough for Mercury to capture you. The clock would tick in years, not months, because every loop is doing work your rocket engine cannot afford to do with fuel. This long approach is not just a stylistic choice. It is what happens when you push against the Sun's gravity with limited delta V. Falling inward is easy, you just let gravity pull you. Climbing back out or slowing down enough to match a tiny planet's orbit close to the Sun is the expensive part. So mission designers look at the budget and say, we cannot afford to burn that much propellant, we will use planetary flybys instead. That choice stretches a few month distance into a 7-year mission. Now, ask the obvious question, what would it take to actually go fast to Mercury and also stop there? You would need propulsion that can accelerate and decelerate over long periods without running out of fuel immediately. High-power ion engines are one option, pushing gently but continuously for months or years with much higher efficiency than chemical rockets. Nuclear thermal rockets are another option, heating propellant with a reactor so the exhaust speed is higher and your delta V per pound of fuel is much better. With engines like that, you could plan a more aggressive trajectory. Instead of bouncing around the inner solar system using planetary flybys to bleed speed, you could dive inward more directly, then use continuous thrust to brake as you approach Mercury. The raw distance to cross, at Mercury's closest, is not huge compared to the outer planets. If you could live in that tens of thousands of miles per hour regime, with steady acceleration and braking, the travel time could drop from years towards something closer to the simple shuttle speed estimate, on the order of a few dozen days. The physics allows it. The gap is in technology, power systems, and again, what we are willing to pay and risk. This is the first planet that really hammers home an important lesson for your mental picture of the solar system. Closer does not automatically mean faster to reach. Mercury is closer in terms of miles, but harder in terms of energy. What really matters is how deep you go into the Sun's gravity well, how much orbital energy you have to get rid of, and how much engine you bring to fight that. If your propulsion is weak or fuel hungry, you pay with years of careful flybys and slow spirals. If your propulsion is strong and efficient, you pay with hardware complexity and risk, but you get your time back. So now you have seen one extreme, a nearby planet that costs you almost a decade if you want to orbit it with today's tech. The obvious next question is, what about the other easy neighbour, the one that really is quick to reach in terms of travel time, but turns into a nightmare the moment you arrive? How can the fastest planet to reach also be the one that basically kills everything you send there in minutes? If you only care about how quickly you can say we made it, Venus wins. Missions have hit Venus in about 4 to 6.5 months. Venus Express took roughly 5 months to arrive, Akatsuki took about 6.5 months. The Soviet Venera landers, several of them, made the trip in roughly 4 to 4.5 months. If you average those numbers, you land at something like 160 days, around 5.3 months. On a travel time scoreboard, Venus looks easy, almost convenient. The reason the clock looks so friendly is straightforward. Venus orbits closer to the Sun than Earth, but not by much, so the distance between Earth's orbit and Venus's orbit is smaller than for any other planet. That means the classic Hohmann transfer orbit between Earth and Venus is short. You leave Earth, you fall inward a bit. Your path intersects Venus's orbit in a matter of months, not years. The geometry is on your side. Less difference in orbital radius, shorter transfer time. On the way there, nothing about the timing is mysterious. The shock comes when you look at what happens when you actually arrive. Venus has a massive atmosphere. At the surface, pressures are over 90 times higher than on Earth, like being almost a mile under the ocean. Temperatures sit around 860 degrees Fahrenheit, hot enough to melt lead and destroy most materials very quickly. The air is mostly carbon dioxide with clouds of sulfuric acid higher up. So yes, you get there fast, but the environment is so extreme that landers survive for minutes to, at best, a couple of hours before they fail. The mission clock split cleanly into two categories, orbiters and landers. Orbiters like Venus Express and Akatsuki ride that few-month transfer, then spend months to years gradually adjusting their orbits. They fire their engines near closest approach to slow down just enough to be captured. Then they use small burns and sometimes atmospheric drag to reshape their path into a science orbit. Most of their time budget after arrival is spent on fine-tuning, mapping and long-term observation from above the atmosphere, where the temperatures and pressures are manageable. Landers live in a totally different world. Venera 7, 8, 9, 10, 13, 14 and others rode the same basic 4 to 6 month cruise from Earth to Venus. But once they entered the atmosphere and headed for the surface, their clock started running out almost immediately. Venera 7 survived for less than an hour on the surface. Venera 13 lasted a bit longer, on the order of 2 hours before the heat and pressure destroyed its systems. So when you ask, how long to Venus, you have to be precise. It is months to get there, and then, if you go all the way down, minutes to live. Now put yourself inside one of those spacecraft for a second. Not in a poetic way, just in terms of what actually happens. You approach Venus at tens of thousands of miles per hour. At some point, you hit the top of the atmosphere. You do not gently enter it, you slam into it. The air in front of you compresses and heats up, your heat shield takes the load, and you start shedding speed very quickly. That thick atmosphere becomes your brake. It lets you save fuel on arrival, because the air does a huge amount of work that your engines do not have to do. But that free braking is not free for your hardware. The thermal stress is brutal. Temperatures on the heat shield spike, the outer layers char and ablate, material peels away on purpose to carry heat with it. The deceleration can be several times Earth gravity, pushing on every structure inside the vehicle. The thicker the atmosphere and the faster you hit it, the shorter your braking time, but the harder the punishment on the spacecraft. Venus lets you trade time in space for stress on arrival. You can arrive fast and brake quickly, but you pay in heat load, structural strain, and shortened hardware lifetime. Orbiters manage this by not going all the way down, and by using a mix of engine burns and gentle aero braking over many passes. They dip into the outer atmosphere just enough to bleed a little speed, then climb back up, then repeat that over and over. Each pass shaves a bit off their orbit, stretching the arrival process over months instead of minutes. Landers don't have that luxury. Once they commit to the descent, it's one shot. Parachutes, heat shields, maybe retro rockets, then direct contact with a surface that is hot enough to overpower their cooling systems very quickly. Now, imagine you had better engines and more power. Suppose you used a continuous thrust drive, like an advanced ion engine with a lot more power than we fly today, and you did not care about going into orbit or landing, you just wanted a very fast flyby. You could leave Earth, accelerate gently but constantly, swing past Venus in something closer to weeks than months, and then keep going. The shorter trip comes from staying under thrust instead of coasting. You're not limited to the classic Hohmann ellipse anymore. You can pick a more direct, higher energy path. But pushing the clock down like that creates a new problem. When you blow past Venus at that kind of speed, your time near the planet is tiny. Your instruments have seconds to minutes of close-range data collection instead of hours or days. You have less time to point cameras, less time to send data back, less time to do any course corrections if something is off. High-speed flybys are great for raw travel time, but they are bad for detailed, careful science. You gain speed, you lose interaction. So Venus ends up being a kind of sharp contrast in the story. It is fast to reach in terms of cruise, but punishing to explore up close. The orbit geometry works in your favour for travel time. The environment works against you for survival time. That split matters when you think about future crewed missions. Nobody is seriously planning to send humans to the surface of Venus with current or near-term technology because the environment is so extreme. In practice, Venus is a quick trip with robots and a hard no for people. And that sets up the next big step. If Venus is the quick but deadly neighbour, what about the world that is slower to reach but actually shows up in serious plans for human landings, bases, and long stays? What does going to another planet really mean to you when that planet is Mars, not just for a robot, but for you as a person? Mars is the first world we actually talk about putting boots on. Not a distant dream, but a real, active plan. NASA and other agencies work with numbers like 7 to 10 months one way, then a total of roughly 3 years for the full mission, when you include waiting on Mars for the next return window and the trip back. Mars becomes the basic question: how long are you willing to be away from Earth, away from gravity, away from normal life? Look at what we have already done. The idea of about half a year to Mars is not guesswork. It is stamped into real missions. Spirit, one of the Mars rovers, spent about 179 days in cruise. Opportunity, its twin, took around 201 days. Mars Reconnaissance Orbiter did roughly 210 days. Phoenix, headed for the Martian North, took about 295 days. Curiosity, the big rover that landed with the Sky Crane, cruised for about 253 days. Maven, an orbiter studying the atmosphere, was out there for around 10 months. When people casually say it takes about 6 to 10 months to get to Mars, they are summarizing these actual clocks. We have literally been sending hardware that drifts between planets for that long. So why does it still take so long if Mars averages only about 140 million miles away from Earth? First, that 140 million miles is an average. The distance changes, but more importantly, you are not flying straight across a gap like an airplane on a line between two cities. You leave Earth, then you follow a curved path around the Sun. That path has to intersect Mars's orbit at the right place and time. The curve is longer than the shortest straight line you could draw between Earth and Mars at any given moment. On top of that, your propulsion is limited. You do not burn engines the whole way. You do one big burn to leave Earth, maybe a few small corrections, and then you coast. Your average speed ends up in the tens of thousands of miles per hour. Impressive, but nowhere near any serious fraction of the speed of light. In other words, most of the time your ship is just falling along a chosen path in the Sun's gravity, not pushing. You have enough delta V to get on the right path and to slow down at the end, but not enough to constantly accelerate. That is why the transit time stays in the months range. You can't just double your speed without paying for it in fuel, mass, and cost. Now bring humans into this. For a crewed Mars mission, your calendar breaks down into a few key blocks. First, you have around 1 day to reach low Earth orbit and check out the systems. That is your starting point, circling Earth at about 17,500 miles per hour. Then, at a carefully chosen time in that orbit, you fire the main engine for a trans-Mars injection burn. That burn is short, something like 6 to 10 minutes of hard thrust, but it changes everything. It takes you off your circular Earth orbit and throws you onto a path that reaches out toward Mars. After that, life slows down brutally. You spend something like 210 to 300 days coasting in deep space. No big engine burns, just small corrosions now and then. Every day is microgravity, radiation from space, constant monitoring of life support, and a tight routine to keep your body from breaking down. You are far from any easy rescue. Then at the end you hit the critical phase, about 20 to 30 minutes of Mars orbit insertion, or entry, descent and landing, depending on your mission profile. In those minutes, you either slow down correctly and arrive safely, or you don't. Months of coasting capped by a short high-pressure window where everything has to work. That is your how long in real human terms. It is not just a distance and a speed, it is months of being locked into a hostile environment, with a few points where the risk spikes sharply. For a full mission, you then wait on the surface or in orbit for the next launch window, roughly a year to a year and a half, then do the same sequence in reverse to come home. Add it all up, and you are looking at something close to 3 years of your life tied to one mission. So why do we keep talking about better engines, and what difference would they actually make? If you could maintain even a tiny continuous acceleration, just a few hundredths of Earth gravity, using something like nuclear thermal propulsion or high-power electric engines, the transit time to Mars changes completely. With constant acceleration for the first half of the trip and constant braking for the second half, some estimates put Mars trips down into the range of a few dozen days, rather than hundreds. You would leave Earth, speed up gradually but steadily, flip the ship halfway, and then slow down into Mars space. In that scenario, your main problem shifts. It's no longer, can you tolerate being in space for almost a year? It becomes, can you survive arriving at Mars at much higher relative speeds? And can your systems handle the heat and stress of braking that hard? You also have to solve the engineering challenges of running those advanced engines for weeks without failure, and shielding the crew from radiation when you're not just drifting quietly, but pumping energy through big power systems the whole time. The transit is shorter, but the technical and safety demands grow. For now, with the propulsion we actually fly, Mars stays in that 7 to 10 month one-way range. That makes it the reference point for everything else. In a way, every other planet is Mars plus more. More distance, more time in microgravity, more total radiation dose, more boredom, more chances for something to break. If a Mars mission already pushes you to 3 years away from Earth for a full cycle, what does that imply for going to Jupiter or Saturn or even farther out? That is the tension you have to hold in your head. Mars is the first deep space road trip that we are truly planning to take, and it is already long, risky, and hard. So what happens when you aim not for a world that is 1.5 times Earth's distance from the Sun, but for a giant planet 5 times farther out, with a gravity field that punishes every mistake? How do you wrap your head around a planet you could, in theory, reach in about a year, but that we usually take 5 or 6 years to get to on purpose? Jupiter sits about 5 times farther from the Sun than Earth, and NASA keeps the summary simple. With the kinds of missions we actually fly today, it takes roughly 5 to 6 years to get there and go into orbit. Galileo took just over 6 years. Juno took just under 5 years, and that was even with an Earth flyby to boost its speed. But if you grab a basic table using shuttle-like speeds, around 28,000 miles per hour, you get rough travel times of about a year to Jupiter. So why do we not do that? The short answer is cost, risk, and how much punishment you are willing to accept at arrival. Start with the raw distances so you see the scale. When Jupiter is at opposition, roughly on the same side of the Sun as Earth, the distance between the two can be around 390 to 600 million miles, depending on the exact geometry. That alone sounds huge, but your path is not a straight line. A Hohmann transfer, the usual minimum energy arc from Earth's orbit to Jupiter's orbit, is a long, stretched ellipse around the Sun. The total path length is much greater than that closest straight line distance. Even so, your cruise speed is still in the tens of thousands of miles per hour. That combination, long path plus those speeds, turns into years in transit. Not decades, which is impressive given the distance, but definitely not months. Now look at what we actually flew. Juno launched in 2011. It did not head straight out. It first went into a solar orbit, then swung back past Earth in 2013 for a gravity assist, using Earth's motion around the Sun to pick up extra speed. It finally arrived at Jupiter in 2016. That is about 5 years total from launch to Jupiter orbit insertion. Galileo launched in 1989. It uses multiple gravity assists, including Venus and Earth flybys, to gradually build up enough speed to reach Jupiter without needing an impossibly large rocket. It arrived in 1995. That is over 6 years of mission time before it even started its main science phase. Those numbers are not random. They come straight from the delta V budget mission planners had to work with, and the amount of free speed they could steal from Earth and Venus through those flybys. A more powerful launch vehicle, more efficient engines, or more propellant on board could have shortened the trip, but at a higher cost and with more risk. Instead, they chose to save fuel and accept extra calendar time. Getting to Jupiter is only half of the problem. The other half is staying there. Jupiter's gravity is strong. Once you fall into its neighborhood, you pick up a lot of speed. To enter orbit, you have to slow down by a huge amount relative to Jupiter. That means a major engine burn near closest approach. If you arrive too fast, the size of that burn goes up sharply. At some point, the required burn becomes too big for your engines and fuel load. You either need a much larger spacecraft and rocket, or you give up on going into orbit and settle for a flyby instead. That is why we distinguish between fast Jupiter missions that do flybys and slow missions that go into orbit. A flyby mission can afford to show up on a steeper, higher energy trajectory. It does not need to lose as much speed to stay because it never plans to stay. It dives through the Jupiter system, collects data, and then keeps going out of the system. An orbiter has to pay what you can think of as a gravity tax. That tax is the big insertion burn. To keep the burn size sane, you accept slower, more gentle arrival paths, and that pushes your trip time up into the 5 to 6 year range. On top of that, Jupiter brings another problem you cannot ignore: radiation. Jupiter's magnetic field traps charged particles and forms intense radiation belts, far harsher than anything around Earth. Spacecraft electronics take a beating in that environment. Shields, hardened components, and conservative orbits are all used to keep systems alive as long as possible. If you came in on a very fast trajectory, then dove deep into those radiation zones immediately, your hardware would see heavy doses in a short time. For a crewed mission, this would be even worse. The faster you arrive, the more aggressive your approach, the harder it is to shield people for both the crews and the time in Jupiter's neighbourhood. So when mission designers sit down and see that a theoretical 1-year Jupiter transfer exists at shuttle-class speeds, they know what it would take to get close to that. You would need higher effective exhaust speeds, engines that can give you much more delta V per pound of fuel. Advanced nuclear thermal propulsion is one option people study. Powerful electric propulsion driven by reactors or beamed power is another. With those, the 1 year to Jupiter or even less than a year trajectories that show up in tables start to look reachable. You launch, accelerate for longer, cut down the coasting time, and arrive at Jupiter in a human career-friendly time. But then new questions appear. Can you build engines that powerful, that reliable, and that light? Can you carry or deliver enough power without making the spacecraft unmanageably large? Can your structure handle the larger burns and higher speeds? And if you're talking about humans, can you shield a crew against both the interplanetary radiation and Jupiter's radiation for such a high-energy mission? You have shortened the calendar time, but you have pushed the hardware and the safety margins much harder. Right now, the compromise is clear. With today's chemical propulsion, plus some electric thrusters and gravity assists, it makes sense to accept 5 to 6 year travel times for orbiters like Galileo and Juno. That keeps rocket size, cost, and risk within what space agencies are willing to sign off on. It's long, but it fits inside a mission timeline that teams can plan and manage. And remember the mental ladder you're building. Mars is already 7 to 10 months one way, with a 3-year round trip for humans when you include waiting. Jupiter pushes you out to half a decade just to get an orbiter on station. So what happens when you step one rung farther, to a planet almost twice as far out as Jupiter, where the flagship mission we flew needed close to 7 years just to show up and start photographing the rings? How long would you really wait just to see one planet up close? 6 years, 7 years, almost a decade before the main show even starts? Saturn forces you to answer that for real. It orbits about 9.5 times farther from the Sun than Earth does. In useful launch windows, the distance between Earth and Saturn is roughly in the 880 to 950 million mile range. That is almost 1 billion miles. With the missions we have actually flown, the pattern is clear. Saturn orbiters live in the 6.5 to 7 year travel time band. Cassini, the flagship mission to Saturn, took about 6.7 years to arrive. That is the price you pay, in time, to stand next to the rings with a camera. Cassini did not just fire its engine and cruise straight out. The rocket that launched it could not give it enough speed in one shot to reach Saturn and still have fuel for arrival and maneuvers. So the mission team used a very specific gravity assist sequence, often called VVEJ, Venus, Venus, Earth, Jupiter. After launch, Cassini went inward toward Venus, swung by, picked up a change in speed and direction, came back for another Venus flyby, then returned to Earth for another boost, and finally used a Jupiter flyby to gain even more energy and bend its path out towards Saturn. Each flyby changed the craft's velocity without needing huge burns, trading extra calendar years for a manageable fuel mass. That is the pattern you see again and again with outer planet missions, especially to Saturn. You can get a spacecraft there with the launch vehicles you have, as long as you are willing to do a gravity assist ballet and wait. Each assist replaces a chunk of what would have been engine delta V. Without that trick, the propellant you would need grows so large that the mission stops being realistic. With it, you can ride those planetary slingshots until you are high enough and fast enough to reach Saturn's orbit. Here is the key trade: you spend almost 7 years just getting to Saturn, but then you stay. Cassini arrived in 2004 and operated until 2017. That is about 13 years of active science in the Saturn system after those 6.7 years in cruise. So your one-time investment, 7 years of deep space travel, bought you roughly 13 years of close-up data on the rings, the moons, the atmosphere, the magnetosphere. That is a good exchange if you're willing to accept that the people who launch the mission will not be the same people who close it out. Careers turn over while the spacecraft keeps working. This is where you stop thinking in launch and done terms and start thinking in decades. Someone greenlights development. Years later, the mission launches. Nearly 7 years after that, it arrives. Science ramps up and continues for more than a decade. By the time Cassini ended, some of the people involved had spent a big chunk of their professional lives with that mission running in the background. The timeline for Saturn is not we go, we arrive, we come home. It is we commit and we live with this for 20 years. So could you do a quick Saturn mission if you really wanted to? The simple tables that assume speeds around 28,000 miles per hour give rough numbers like 3.6 years to get to Saturn. Those estimates basically scale distance by speed and imagine a fairly direct transfer. Physically, that is not crazy. If you could afford the delta V. In practice, hitting that kind of time would require much more powerful rockets, orbital refueling or radically more efficient propulsion, just to leave Earth with enough fuel on board to go fast and still break into orbit at Saturn. Right now, that kind of high-energy Saturn mission runs into a wall made of money and engineering limits. The physics says it can be done. The budget and risk calculations say not yet. You could also shave time by accepting a flyby instead of an orbiter, showing up on a steeper, faster trajectory, grabbing data as you pass, then heading on to the outer solar system. But you would give up the long detailed study you get from staying in orbit and revisiting the rings and moons over and over. So Saturn becomes the place where deep time starts to feel normal. 7 years to get there, 10 to 15 years of operations. From the first serious design work to the final command, you are looking at a mission that spans a generation. When people answer the question, how long does it take to reach Saturn, they are not just naming a number of travel years, they are also hinting at how long you have to stay organised, funded and focused. Now imagine all of that, and then ask what it would look like if you tried to send humans instead of electronics. A round trip that might eat up a major part of a person's career, maybe more. Years in transit, long exposure to radiation, and a target deep in the outer solar system with no quick way home. With present-day propulsion, a human Saturn mission is not just a technical challenge, it is a life commitment. And that brings you to the next step out, where things get even more extreme. If Saturn already forces you to think in spans of 20 years for one project, what does that mean for a planet even farther out? One we have seen up close exactly once and only for a few brief hours. How weird is it that for one whole planet in our own solar system, we have basically one good close-up, one flyby, one pass, and that's it. That planet is Uranus. Your entire civilization has seen it up close exactly once, when Voyager 2 went by in 1986. That probe launched in 1977 and reached Uranus in about 8 years and 5 months. One launch, one 8.5-year cruise, one brief encounter, and then it was gone, on its way to Neptune. That single mission is still your only real data point for how long to Uranus in actual practice. So when you talk about Uranus travel times, you're mostly talking about that one clock, roughly 8.5 years, and then simulations on top of it. Mission studies that look at current rockets and conservative trajectories give another number, around 13.4 years for a Uranus orbiter and probe with today's tech. That longer time isn't because Uranus is some unreachable edge of the universe. It's because orbiting is much harder than flying by, and the engines you're willing to pay for right now are not insanely powerful. If you want to show up slow enough to be captured into orbit with room for error, you naturally slide into the decade-plus range. Look at where Uranus actually is. It orbits at around 19 astronomical units from the Sun, so about 19 times farther out than Earth. In useful launch alignments, that puts it on the order of 1.8 to 2 billion miles away. That number already feels abstract, but the real impact shows up in the conditions. Sunlight is much dimmer out there. If you try to run a big spacecraft on solar panels alone, you're working with weak power compared to Mars or even Jupiter. That pushes you toward nuclear power sources for electricity and heating. Everything else gets harder too, communications delay grows. Instead of minutes like Mars, you're looking at a signal that can take a couple of hours for a round trip. That means no real-time joystick control, only pre-planned sequences and slow feedback. Thermal management becomes a serious design problem because the spacecraft sits in deep cold, but some instruments and systems need to stay warm. Heaters, insulation, radiators all have to be tuned for a place where the sun is far away and your power budget is tight. So the clock for Uranus is not just the cruise time from launch to arrival, it's also the years of engineering to build something that can live that far from the sun, on low power, with long delays and no hope of rescue or repair. At Mars, you worry about dust, temperature swings, and modest communication delays. At Uranus, you're dealing with a dim, cold environment for well over a decade, plus the long coast through the outer solar system just to reach it. Now think about what a future fast-track Uranus mission would have to look like if you wanted to stop treating it as a once-per-generation event. You swap out simple chemical propulsion for something like nuclear electric propulsion, where a reactor powers high-efficiency ion or plasma thrusters. Those engines don't push hard in the moment, but they can push for months or years, slowly stacking up a very large change in velocity. You fly continuous low-thrust arcs instead of coasting on a single Hohmann-style ellipse. With that kind of drive, you can, on paper, keep a tiny fraction of a g of acceleration and deceleration for long stretches. Even a small, steady push adds up over months. Instead of doing most of the trip as a passenger on a ballistic path, you actually pilot your trajectory, speeding up and slowing down to cut the total time. Those 8 to 13-year travel times start to shrink. Single-digit years become realistic. You might talk about 5 or 6-year cruises to orbit. Not just flybys, maybe even less if you're willing to lean hard on the tech. But as always, when you make time shorter, you make the engineering problem harder. Nuclear electric propulsion means running high-power reactors in space for very long periods, managing heat, radiation, and reliability. Continuous thrust means your engine can't just work for a few minutes. It has to work for years without major failure. A faster trip compresses the schedule, but it also compresses your margins. There's less time to diagnose problems, less time to adjust if something doesn't behave exactly as planned. And then there's the human factor, not for crew on board yet, but for the people on the ground. If you launch a Uranus mission today on a conservative trajectory, your main science payoff might come a decade or more later. If you aim for something like a 5-year fast-track orbit insertion with advanced propulsion, the development time plus cruise still pushes your real scientific harvest into the 2040s or 2050s. That's the pace you are dealing with. Entire careers can pass between initial design meetings and the first high-resolution images coming down from the spacecraft. So the biggest enemy for a Uranus mission is not just distance or delta V, it's patience. Are you willing to fund, build, launch, and support a mission that takes 8 to 13 years just to arrive, and then more years to map the system? Are you okay with a timeline where the people who start the project might retire before the mission hits its stride? At Mars, the feedback loop is relatively quick. You launch, you arrive within a year, and you get headlines. At Uranus, you launch, and for a long time after that, you mostly get status updates and trajectory corrections. This is what How Long to Uranus really asks you. Not just how long does a signal take to cross that distance, or how many miles you have to cover, but how long can you stay focused? If you want real, detailed science at Uranus, with an orbiter and atmospheric probes, you're signing up for a multi-decade effort from first design to last data packet. And once you admit that, you have to face the next step out. If Uranus already demands 8 to 13 years one way, and that's for a mission we still haven't flown, what does it mean to go to the last major planet even farther out, where our only visit so far took 12 years of travel just to get one fast flyby? How do you deal with a planet that you've technically visited, but only for a single high-speed drive-by 12 years after launch, with no second chance? That planet is Neptune. It's the last full status planet in the classic list, and like Uranus, you have only one close encounter on the books, Voyager 2. It launched in 1977 and reached Neptune in August 1989, so about 12 years of travel before that one flyby. That's your real historical answer to how long to Neptune with the kind of mission profile we could fly in the late 20th century. Now look at the distance involved, because it makes Mars feel like a short hop. Neptune orbits at around 30 astronomical units from the Sun, which means roughly 30 times farther out than Earth. In useful alignments, that puts Neptune about 2.8 to 3 billion miles away from Earth. And remember, that's just the straight line scale. The actual transfer orbit, the path Voyager 2 took around the Sun, is even longer, because it bent past Jupiter, Saturn and Uranus along the way. If you take simple tables that assume a speed like 28,000 miles per hour and scale time with distance, you get rough travel times of a little over 11 years to get to Neptune. Voyager 2 basically did that, with gravity assists chained together to shape the path and give it the needed speed. The key is, Voyager 2 did not go straight there. It made use of a rare alignment of the outer planets, something that only happens about once every 175 years. This alignment allowed a so-called Grand Tour, a single spacecraft visiting Jupiter, then Saturn, then Uranus, then Neptune, using each one as a gravity assist step for the next. Every flyby changed Voyager 2's direction and speed in a way that kept pushing it outward without massive fuel burns. That clever path turned one launch into a 4-planet campaign, but it also locked in the timing. If you're going to use Jupiter, Saturn and Uranus to get to Neptune, you accept that the Neptune flyby will happen about 12 years after launch. That is built into the geometry and the sequence of assists, so that 12-year number is not some arbitrary delay. It's the result of a very specific design choice. Use multiple giant planets to carry you outward cheaply, in energy terms, and accept that each step takes a couple of years. By the time Voyager 2 got to Neptune, it had already spent over a decade crossing the outer solar system, and each step was fixed once the mission was designed. It was a one-time shot, born from that rare alignment. What if you aimed straight for Neptune today, with no grand tour, just Earth to Neptune with maybe 1 or 2 assists at most, and you wanted to go into orbit instead of just doing a flyby? Modern mission studies that look at actual propulsion, we can talk about cruise times in the 10 to 15 year range for Neptune orbiters. 10 years is optimistic, 15 is more conservative. That is not just because of the distance, although 3 billion miles is a lot. It's because going into orbit demands that you arrive with a manageable speed relative to Neptune so you can slow down and be captured without insane fuel requirements. To cut that time significantly, you run into the usual problems. You would need a very large rocket or multiple launches and orbital refueling just to get enough propellant into space. You would probably also need advanced propulsion, like nuclear thermal engines or high-power electric drives, to give you the extra delta V needed for a faster, more direct trajectory. All of that pushes cost, complexity, and risk up. So when space agencies rank mission ideas, Neptune orbiters tend to slide downward, not because they are uninteresting scientifically, but because the long travel time dominates budgets and attention spans. Think about what a 10 to 15 year cruise really means for planning. If you approve the mission today, you spend years designing and building the spacecraft. Then you launch, Then you wait a decade plus for arrival. Then you begin the main science phase, which itself could last many years. The total span from first serious design work to final data could easily be 20 to 30 years. That is longer than a lot of careers. People will retire before some of their plans pay off. That's why Neptune is the place where how long stops feeling like just an engineering question and starts feeling like a question about your whole civilization. Technically, you can reach Neptune inside one human career. 12 years is not outside a human lifetime, it's inside it. 10 or 15 years is long, but not impossible. The limiting factor becomes, can your institutions, your funding systems, your public interest stay locked onto a mission that has no big payoff for more than a decade? With Mars, the feedback loop is short. You launch, and within a year you have a new rover on the ground. With Jupiter or Saturn, you still get data within the working life of the people who launched the mission. With Neptune, if you start now, it's your successors, people who are kids right now, who will be looking at the first close-up images from orbit. So when you ask, how long does it take to reach Neptune, you're really asking something deeper. Are you willing to run 20-year, 30-year projects just to fully explore one planet and then do it again for others? The physics says yes, you can. The travel times are long but survivable. The bottleneck becomes patience and long-term planning. And that leads naturally to the next step, because even beyond Neptune, we've already proven that you can cross similar distances faster if you're willing to never stop, to accept a one-way, high-speed flyby of a world on the edge of the sun's influence. So what does that look like when the target is not even a planet anymore, but a demoted world and a belt of icy bodies far beyond Neptune? What happens when you stop trying to play it safe and just throw a spacecraft at the outer solar system as fast as you possibly can, even if it means you will never stop when you get there? Pluto is where you see that in action. It is not counted as a planet anymore, but the New Horizons mission gave you one of the clearest lessons about raw travel time versus what you can actually do when you arrive. New Horizons launched in 2006. It got a huge kick from its launch vehicle, then another boost from a Jupiter flyby in 2007, and reached Pluto in 2015. That is about 9.5 years to cover almost Neptune-level distances. In outer solar system terms, that is fast. The trick was simple but aggressive: very high escape speed off Earth, plus a gravity assist from Jupiter, and absolutely no plan to slow down at Pluto. That last point is crucial. New Horizons was designed as a flyby mission from the start. Its fuel was for course corrections and small tweaks, not for major braking burns. There was never any intention to go into orbit around Pluto. Instead, the mission was set up as a one-shot pass, race in, grab as much data as possible during a narrow time window, and then keep going outward. That is why the 9.5-year number can be misleading if you do not look closely. 9.5 years to Pluto sounds like we suddenly figured out how to reach the edge of the solar system much faster than it takes to reach Neptune. In reality, you only get that time because you accept that you will not stop. If you tried to design a Pluto orbiter, the picture changes completely. Going into orbit around Pluto means you have to cancel almost all of that high approach speed. That requires a huge amount of delta V. With chemical rockets, that would translate into a massive fuel load, which means a huge launch vehicle, or multiple launches and assembly in space, or much slower, lower energy trajectories that give you more time to brake gradually. Either way, you pay. You either pay in more fuel and cost, or you pay in more cruise time. You cannot have 9.5 years to Pluto and then a nice comfortable orbit with the same propulsion profile New Horizons used. So the fast number New Horizons gave you is tied directly to the fact that it was a flyby. It passed Pluto at a relative speed of tens of thousands of miles per hour. The closest approach lasted minutes. The window for the highest resolution images and the best instrument data was measured in days around that closest pass. After 10 years of travel, the most intense science moment was over in a tiny fraction of that time. The rest of the mission is data playback, extended science, and continued cruise into deeper space. Then there is the Kuiper Belt, which is basically the region beyond Neptune filled with small icy bodies. After Pluto, New Horizons did not stop. It kept going and targeted another object, Arakoth, which it flew by in 2019. The way you should think about travel time to Kuiper Belt objects is simple. It is time to Pluto, plus however long you're willing to wait for alignment with the next target. You're already out there, so changing course slightly to hit another small body is doable. But each detour adds more years. As you go farther out, decades stop being unusual and start being standard. At that point, this is what your timeline looks like. Launch in 2006, reach Pluto in 2015, reach a Kuiper Belt object a few years after that. Keep moving outward until the spacecraft eventually runs out of power. From the first design work to the last useful signal, you're talking about a project that spans a large piece of a human life. This is what normal starts to mean in the outer solar system if you go for high-energy, one-way missions. You accept that the travel and the gaps between big events are long, and that the real science payoff comes in short bursts when you pass each target. Now, why does any of this matter when you go back to thinking about planets instead of dwarf planets and small bodies? Because Pluto and the Kuiper Belt show you one extreme of the trade space. If you choose fast, high-energy, one-way flyby profiles, you can bring the outer solar system into a human-friendly travel time. You can get to Pluto in under 10 years. You could, in principle, do similar things for the giant planets. With a big enough rocket and the right trajectory, you could design missions that hit Jupiter, Saturn, Uranus or Neptune much faster than the orbiters we've flown so far. But you would pay the same price New Horizons did. You arrive fast, you do not stop, and your close interaction with the target is very short. You might spend 5 or 6 years getting to Jupiter on a slow path and then 10 years in orbit mapping everything in detail. Or you might spend 1 or 2 years getting there on a very fast path and have only hours to days of close-up data before you move on forever. Those are two completely different types of mission. One optimizes for long-term science at one world, the other optimizes for hitting multiple targets quickly at the cost of depth. Pluto and the Kuiper Belt objects are basically your demonstration missions for what the solar system looks like when you push speed and accept that you will just keep going. They show that you can reach extreme distances in under a decade if you commit to never slowing down. They also show that when you do that, your how long to get there number stops telling the full story. The real question becomes, how long do you get to stay in the interesting zone, and how much of a 10-year journey is spent on a single intense week? That difference matters once you start thinking about sending people, not just machines. A human can physically survive a 10-year round trip if everything works. But does it make sense to send a crew on a mission where the whole point of arrival is over in a few minutes or days, and then they are stuck coasting again for years with nothing new to see? For robots, that trade is fine. For humans, it may not be. So the Pluto and Kuiper Belt story is not just a side note, it is a warning and a hint. You can slash travel times if you go high energy and treat every world as a one-way flyby. Or you can slow down, accept longer times to arrival, and get real time on target with orbiters and landers. You cannot avoid that choice. Every how long does it take number you see hides that trade underneath. And once you understand that, you can no longer talk about travel time without talking about who is on board. Because the moment you put people in the loop, the clock stops being just about engines and gravity and starts being about how long a human body and mind can actually live in that environment without failing. How far out into the solar system can you really go? Not your probe, you, your bones, your brain, your lifespan. It's one thing to bolt electronics to a tank of fuel and let it cruise for 12 years. If a sensor fails, you lose data. If a heater dies, you shrug and write a paper about it. Put a human in that same timeline and the question changes instantly. Radiation, bone loss, muscle atrophy, isolation, stress, limited medical care, all of that turns how long to Jupiter into how much of a human life can you safely spend in transit before something breaks that you can't fix. Mars is the first real test case though. NASA's planning numbers for a classic Mars mission are roughly 3 years door to door. You spend several months going out, somewhere in the 7 to 10 month range. You stay on or around Mars for more than a year, because you have to wait for the next good launch window back. Then you spend several more months coming home. For that entire time, you're either in microgravity, in partial gravity that is only about 38% of Earth's, or strapped into exercise machines trying to keep your body from degrading. Over that 3-year arc, you take a non-trivial dose of cosmic rays, the high-energy particles that constantly sweep through space. You live with the risk of solar flares and coronal mass ejections, sudden bursts of radiation from the sun that could dose a crew badly if they're not inside a well-shielded part of the ship. Your medical kit is limited. You can't do major surgery, you can't evacuate to a hospital, you manage bone density loss, muscle loss, changes in vision, immune system shifts, and psychological strain in a small, closed environment. Now take that Mars profile and stretch it to Saturn or Jupiter with today's propulsion. Instead of 3 years round trip, you are looking at something that could easily push toward a decade per crew if you tried to keep the same style of mission: outbound cruise, operations phase, inbound cruise. Even if you tried to cut the surface or orbital stay and just do a brief science phase, your travel legs alone are years each way. The health issues that are already serious for 3 years start to stack up in ways that are hard to predict over 7, 8, 9 years. On top of the biology, life support quietly becomes the real-time limiter. Every extra year you add to a mission multiplies the demands on your systems. You need more food, or more reliable ways to grow or recycle it. You need closed-loop water systems that can run for years without major failures. You need air recycling that can handle component wear, contamination, and unexpected problems. You need spare parts for everything that can break, and you need tools and knowledge to repair things you didn't plan to repair. Reliability also isn't linear with time. A machine that you're confident will run for 2 years without catastrophic failure might not look so good when you ask it to run for 10, so you either overbuild, which adds mass, or you accept more risk. Every extra year in transit doesn't just add 1 unit of difficulty, it pushes you up a curve, where complexity, spare parts, mass, and psychological pressure all increase sharply. That's why cutting travel time is not just about comfort, it's a survival strategy. A faster engine is, in practice, also a radiation shield and a health shield, because less time in deep space means fewer radiation hits and fewer years of living on the edge of your system's reliability. Faster propulsion changes the biology equation without changing biology itself. If you can cut a Mars trip from 9 months to 6 weeks, the dose of cosmic rays drops. The cumulative bone and muscle loss in microgravity drops. The wear on life support drops. The probability that some low probability failure happens somewhere in the chain goes down. The same logic scales up brutally for the outer planets. With current chemical propulsion, a Jupiter or Saturn mission with humans is right at the edge of what seems possible in terms of life support and health. With advanced propulsion that can keep travel times for those targets under, say, 2 or 3 years each way, the problem looks less insane. When you push farther out to Uranus or Neptune, today's propulsion makes crewed missions almost absurd. You're talking about one-way cruise times in the 8 to 12-year range, even for relatively aggressive trajectories. That's just to arrive. If you want a crew to do anything meaningful and then come home, you're looking at mission durations that eat a huge fraction of a human life. You would launch as a young adult and return in middle age, assuming nothing serious went wrong with your health or the ship in the meantime. And those are just the calendar numbers. Overlay the biological risks on that. 8 to 12 years of intermittent microgravity and partial gravity, years of radiation exposure, years of living in a confined space with the same small group of people, years of hardware cycling through thermal changes, vibrations, and wear. The odds that every system behaves perfectly the entire time are not high. The odds that human health follows the neat curves you see in short-term studies are not guaranteed either. A single major failure far from Earth would likely be fatal, because rescue would not be an option. So when you hear "how long to the outer planets," and you imagine yourself on board with propulsion similar to what we use now, the honest answer is basically longer than we're willing to risk. For robots, 10 to 15 years of cruise plus long operations is acceptable. For crews, it is not just a stretch, it is a different category of mission, one that current agencies are not planning to attempt. With today's tech, the outer planets are robot-only zones. humans are realistically limited to Mars and maybe, far in the future, missions that skim the inner edge of the outer system with very advanced propulsion and life support. That's why every serious conversation about humans going farther than Mars comes back to engines and travel time. If biology and psychology put a hard cap on how long you can safely stay in deep space, then the only way to open up the rest of the solar system to people is to crush the clock. Not by changing humans, but by changing how fast and how efficiently you move them. And that brings you to the real pivot in this whole story. If the current rockets lock you into mission clocks that are too long for humans and barely manageable for robots, what happens the moment you swap those rockets for something with much higher performance? Something that can turn years into months and months into weeks? What happens to everything you've heard so far if you simply change the engine? If you stop assuming chemical rockets with short burns and start assuming drives that can push for months? Up to this point, every how long has been built on the same base. Chemical propulsion with maybe a small electric assist. That gives you Mars in 7 to 10 months, Jupiter in 5 to 6 years, Saturn in almost 7, Uranus and Neptune in roughly a decade. Swap that propulsion for nuclear thermal, nuclear electric or high-power ion drives, and in principle those same planets move much closer on your mental map. Years drop toward months, months drop toward weeks. Start with something we have already flown, ion engines. Missions like Deep Space One and Dawn used ion thrusters that produce very small thrust, but they do it almost continuously. Instead of a few minutes of strong push, you get weeks, months, sometimes years of gentle but steady acceleration. The thrust at any instant is tiny. You could overpower it with your hand if it were pointed at you, but over time the change in speed adds up to huge values. Dawn used this to move from one asteroid to another, reshaping its orbit around the Sun in ways that would have been impractical with chemical rockets. Now imagine using that mode of operation for a Mars trip. Instead of doing a single big burn to leave Earth and then coasting for 210 days, you accelerate for part of the way, then flip and decelerate for the rest. At constant low acceleration, your maximum speed during the trip goes up and your total travel time goes down. Some estimates show that if you had enough power for strong ion or plasma drives, Mars transit times could drop from hundreds of days down into a few dozen days. The trick is not magic physics. It is simply pushing longer instead of accepting a long coast. Nuclear thermal rockets attack the problem from another angle. Instead of burning chemical fuel in a combustion chamber, you run a reactor and use its heat to accelerate propellant out the back. That gives you exhaust speeds roughly double what you get from the best chemical rockets. In plain language, each pound of propellant can give you roughly twice the change in speed. That means your total delta V budget for a given fuel mass is higher. With more delta V, you're no longer forced into minimum energy Hohmann transfers. You can afford higher energy trajectories. You can leave Earth faster, bend your path more, arrive sooner, and still have enough margin left to slow down at the other end. This doesn't break any laws of physics, it just uses a different way of turning mass into a fast exhaust stream. Nuclear thermal systems were studied seriously decades ago and tested on the ground. The difficulties are safety-related and engineering-related, not basic physics. If you can solve shielding, reactor reliability, and safe operation in space, you can build a propulsion system that reshapes interplanetary timelines in a very direct way. Then you have the more speculative but still physically valid options, like fusion drives, antimatter-driven concepts, and beamed sails. Solar sails and laser-pushed sails skip propellant entirely. You push a large reflective surface with light, either from the sun or from powerful lasers. Over time, that push can get a spacecraft to speeds of hundreds of thousands of miles per hour or more. Some paper studies show effective cruise speeds that could reach into the range where decade-scale trips to the outer planets fall to year scale or less. Fusion and antimatter concepts go even further in theory. The energy density of fusion fuel or antimatter is vastly higher than chemical fuel. If you could build engines that control and direct that energy safely, you could create exhaust streams at extremely high speeds. That translates into enormous delta V with relatively small amounts of mass. In that regime, trips that now take 10 or 15 years could, on paper, drop to a year or less. The limiting factor is no longer the fundamental physics. It is our ability to engineer, contain, and control these reactions reliably on a spacecraft. The important point is this: none of these advanced drives change orbital mechanics. The planets are still moving on ellipses, launch windows still exist, gravity still shapes paths. What changes is your freedom to ignore the slow, fuel-efficient options. With a high-performance engine, you can choose to leave at less perfect times, you can correct more in flight, you can skip complicated gravity assist chains, and you can show up with enough propulsive power to brake hard into orbit without needing decades of setup. Even then, launch windows do not disappear. They just become less strict. If you have a powerful engine, there will still be times when leaving makes more sense, when you can take advantage of geometry to minimize the energy cost. The cheapest and shortest options will still cluster around those alignments. You will still talk about good and bad years for a Mars or Jupiter mission. But if you miss the perfect window by a bit, you won't be forced into adding a whole extra year. You'll have enough delta V to fix timing errors without completely wrecking the mission profile. So how long never turns into a pure question of raw engine power. It stays a balance between how much thrust and delta V you can afford and how smartly you use orbital geometry. Better drives change the scale. They bring Mars into the few-week range. They bring Jupiter and Saturn into the 1 to 2 year zone. They pull Uranus and Neptune down from half a career to serious mission but still within a working life. But they don't erase the underlying structure. And that leads to one more point you can't ignore. Many of the clever tricks we use today, like gravity assists, were invented precisely because our engines are weak and fuel-hungry. They let us steal energy from planetary motion instead of burning it in propellant. If you suddenly had engines that could easily deliver huge amounts of delta V, would those tricks still matter? Or would you just brute force your way across the solar system? To answer that, you need to look directly at gravity assists themselves, not as curiosities, but as a core part of the way we've hacked the solar system's energy system to make slow rockets do big things. How do you feel about free speed if the price you pay is years of your life? That's the real deal behind gravity assists. They are the cheat code under half the travel times you've heard in this video so far. Galileo, Cassini, Juno, Voyager, New Horizons, all of them leaned hard on this trick. You dive past a planet, let its gravity pull you in, swing around it and leave going in a different direction, often faster or slower relative to the Sun, all without burning a big chunk of fuel. On paper it looks perfect, extra speed with no propellant. In reality, you buy that free speed with calendar time, usually several extra years added to your mission. Here's what's actually going on. Each planet is not just sitting there, it's moving around the Sun at tens of thousands of miles per hour. When your spacecraft falls into a flyby, you borrow a tiny bit of that orbital momentum. To an observer sitting on the Sun, your speed and direction change. If you pass behind the planet in its direction of travel, you leave with more speed relative to the Sun, a boost. If you pass ahead of it, you can leave with less speed, a brake. From your perspective on the spacecraft, you burned no fuel for that major change, so it feels like you got something for nothing. From the planet's perspective, it lost or gained a minuscule amount of momentum, too small to matter. Look at how that plays out in real missions. Galileo, heading to Jupiter, used multiple gravity assists. It didn't just light its engine and cruise out. It did Venus and Earth flybys to build at enough speed to get to Jupiter with a launch vehicle that would have otherwise been too weak for a direct high-energy injection. The trade. About 6 years of travel time before Jupiter orbit insertion. Cassini went even further with the VVEJ path. Venus, Venus, Earth, Jupiter. Each of those flybys changed its speed and stretched its orbit farther out. By the time it headed towards Saturn, it had used the inner planets and Jupiter like stepping stones. The price, about 6.7 years from launch to Saturn arrival. Juno shows another version. It launched from Earth, went into a solar orbit, then came back for an Earth flyby 2 years later. That flyby gave it the extra push it needed to reach Jupiter on the rocket it had. Total travel time about 5 years. Voyager 2 is the extreme case, the whole solar system cascade. It left Earth, swung by Jupiter, then Saturn, then Uranus, then Neptune. Each flyby shaped its path and sped it up or redirected it so that one launch turned into a 4-planet tour. But that chain of assists locked in the schedule. Around 8.5 years to Uranus, about 12 years to Neptune. Once you commit to that sequence, you commit to the long timeline that comes with it. All of these missions had the same basic problem. Their rockets and fuel loads could not give them the huge direct delta V needed for a fast straight shot and a big braking burn at the end. Gravity assist let them trade fuel for time. You get the speed changes you need, but you have to wait for the right alignments and accept the long flight paths that go with them. You're orbiting the Sun. The planets are orbiting the Sun, and to hit each target at the right time and place, you follow a path that looks like a multi-stop flight instead of a direct ticket. Then you get to Mercury, which flips the intuition in a different way. For outer planet missions, gravity assists usually speed you up, kicking you outward. For Mercury missions, you use assist to slow down. As you fall inward toward the Sun, your orbital speed goes up. Reaching Mercury isn't the hard part. Arriving slow enough to be captured is the hard part. So missions like Messenger and Bepi Colombo use flybys of Earth, Venus and Mercury itself to bleed off orbital energy. Each pass steals some of your speed relative to the Sun, twisting your path so that over years you gradually match Mercury's orbit more closely. Here, gravity assists are like taps on the brakes spread out over years. Doing all that braking with the engine burns would require a fuel load that's not realistic with current launch vehicles. So again, you trade fuel for time, you get to Mercury orbit, but it takes you roughly 7 years of looping through the inner solar system to do it. Same cheat code, different goal, less speed instead of more speed, same basic cost in calendar years. Now think back to the future drives you just heard about. Nuclear thermal, nuclear electric, high power ion, maybe even something like beamed sails or fusion in the far future. If those engines become real and reliable, the way we use gravity assist changes. With high thrust and high efficiency, you can start proposing missions that skip the long chains of flybys. You could, for example, launch a Jupiter orbiter that goes on a much more direct, high-energy trajectory, then relies on a powerful drive to handle the brutal orbit insertion burn itself, instead of letting a gravity assist do most of the heavy lifting. In that regime, you're paying in fuel what we currently pay in time. You carry more propellant, you build a more capable propulsion system, and you do big burns instead of waiting years for the right planetary alignments. Gravity assists don't disappear. They're still useful tools to trim delta V and fine-tune trajectories, but they stop being mandatory for outer planet missions. They become one option among many, not the default choice you're forced into by weak engines. Until that happens, though, gravity assists are not going anywhere. As long as you're working with chemical rockets and modest electric propulsion, and you want to reach the outer planets without launch vehicles the size of skyscrapers, you're going to be slingshotting. That is why a Jupiter orbiter is 5 to 6 years, a Saturn orbiter is almost 7, a realistic Uranus or Neptune orbiter is a decade or more. The physics gives you a way to reach them with the rockets you have, and the price is time. And that brings you to the last piece of this picture, one that pulls everything together. Now that you've seen how engines, geometry, assists and biology all fight over the clock, how do you sum up how long it takes in a way that actually means something from a human point of view, not just a mission chart? If you lay your whole life out as a line, where do the planets actually fit on it? Not as ideas, but as real chunks of time you'd lose? Mars takes months. Jupiter takes 5 to 6 years. Saturn takes about 7. Uranus sits in the 8 to 13 year band. Neptune pushes into the 10 to 15 year range, depending on how aggressive your trajectory and propulsion are. A full robotic grand tour of the outer planets, plus a couple of Kuiper Belt targets, fits comfortably into half of one human lifetime if you start counting from launch. A crude version of that with today's tech does not fit. Not safely, not yet. Look at what's already on the books so you don't think any of these numbers are just theory. In roughly the last 60 years, you've seen Venus reached in a few months over and over. You've seen Mars reached in a few months again and again. You've seen Jupiter and Saturn reached in a handful of years, with orbiters and flybys. You've seen Uranus and Neptune reached in about a decade through Voyager 2's trajectory. You've seen Pluto, which sits near Neptune's distance, reached in under 10 years with New Horizons. These timelines are not guesses on whiteboards. They are stamped into tracking data, mission logs, and press releases, so the clock is real, and we already know how it behaves with current propulsion and typical risk tolerance. We also know what would blow that whole picture up. The day you see a Mars mission that goes from Earth to Mars in weeks instead of months, not as a paper study but as an actual flight, the whole idea of far shifts. Suddenly, 7 to 10 month trips don't look like the baseline anymore. They look slow and outdated. The moment you see a Jupiter orbiter that launches and arrives in 1 or 2 years instead of 5 or 6, your sense of the outer solar system compresses. Jupiter and Saturn stop being places previous generations might have dreamed about and start looking like campaigns you could lead and finish inside one career. The technical changes that would make that happen are not mysterious. Faster, more efficient propulsion that can provide continuous thrust. Better radiation shielding, both passive and active. More robust life support that can run for years with closed loops. Automation and autonomy that lets small crews or even single pilots manage complex chalets without huge ground control teams. Each one of those upgrades shaves time off missions or makes long duration safer and more tolerable. Put them together, and the numbers you've heard throughout this video start dropping. But you came in with a very simple question, and now you're ready for a direct, final answer that includes all the nuance we've built up. So with today's technology and typical mission designs, how long does it take to reach each planet in our solar system? Mercury first. If all you want is a flyby, you're looking at a few months. Mariner 10 did its first Mercury flyby after a timeline measured in months, not years. But if you want to actually orbit Mercury with today's propulsion and smart but conservative trajectories, you're in the 7-year range. Messenger did roughly that. Bepi Colombo's on a similar clock. Same distance, radically different time depending on whether you just pass by or slow down. Venus next. Venus is straightforward on travel time, about 4 to 6.5 months one way. Many Venera missions, Venus Express, Akatsuki, they all sit in that zone. If you want one clean number, you can say roughly 5 months is typical. Fast to reach, brutal to survive on the surface. Mars is your main reference. In practice, actual travel times have ranged from about 128 days up to around 360 days, depending on launch window and trajectory. When people plan human missions, they talk about 7 to 10 months one way, not because they like rounding, but because that captures most realistic profiles we can run with current rockets. So Mars is about half a year to a bit less than a year in cruise under normal plans. Jupiter. For flybys, if you really push and take higher energy paths, you can aim for around 3 years or so as a rough lower bound. For orbiters, with the kind of missions we've actually flown, you're in the 5 to 6 year band. Galileo and Juno both landed there. So how long to Jupiter is 3 years if you just want to pass fast and not stop, and about 5 to 6 years if you want to go into orbit and stay. Saturn. Cassini is your benchmark. It took about 6.7 years to arrive and go into orbit. When people list typical Saturn orbital mission times, they sit in the 6.5 to 7 year range. Faster, more direct options exist in theory, but they're not what we've chosen to fly yet. So call it roughly 7 years to orbit Saturn with today's style of mission. Uranus. You only have one real data point from history, Voyager 2's flyby about 8.5 years from launch to arrival. Mission studies for a dedicated Uranus orbiter using conservative trajectories and current propulsion give numbers in the 10+ year range, often around 13 years. So it's fair to say around 8.5 years for a fast flyby, and around 10 or more years if you want to settle into orbit and do serious long-term science. Neptune. Voyager 2, again, is the historical anchor, about 12 years to reach it using a Grand Tour gravity assist chain through Jupiter, Saturn and Uranus. That's a flyby, not an orbiter. A dedicated Neptune orbiter with today's tech would likely sit in the 10 to 15 year cruise range, depending on how aggressive you are with trajectory and propulsion. So you can treat around 12 years as the real-world example for a well-designed flyby profile, and similar or longer for any mission that wants to stay in orbit. So your final summary looks like this, in plain language. Mercury, months for a flyby, about 7 years for orbit with current rockets and gravity assist strategies. Venus, about 4 to 6 months. Mars, roughly 128 to 360 days in practice, and 7 to 10 months as the usual planning number for human missions. Jupiter, about 3 years for fast flybys, around 5 to 6 years for orbiters. Saturn, roughly 6.5 to 7 years to get an orbiter on station. Uranus, about 8.5 years for a flyby like Voyager 2, and 10 or more years for serious orbital studies. Neptune, about 12 years with a Grand Tour flyby path, and similar or longer for any future orbiters. Right now, those numbers feel big because they are big. They force you to think in mission timelines that stretch over chunks of a life, but they are not carved into the universe. They are the numbers you get when you combine current propulsion, current risk tolerance, current budgets, and current ambitions. Every step you take in propulsion, shielding, life support, and automation pushes those numbers down. A Mars mission that drops from 8 months to 6 weeks changes what far means in your head. A Jupiter orbiter that arrives in 2 years instead of 6 changes who can reasonably expect to see the whole mission through. A Neptune orbiter that arrives in 7 years instead of 12 shifts it from a once-per-generation gamble into something that fits inside a single extended career. Today, the solar system takes years to cross. Tomorrow, if you decide to push the engineering hard enough, those same distances can be compressed until Mars feels like a long trip, not an ordeal, and Jupiter feels like something you could step away for, the way people talk about a long assignment or a sabbatical. The limits are not just in space, they are in what you choose to build. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.